Welcome back, quantitative analysis students. Now we're going to talk about chapter 5.2, which is logarithmic functions and their properties. In this section, we're going to talk about how to do regressions with exponential functions once more, and we're going to include the idea of log mode, and we're going to talk a little bit about what log mode is. When we were doing our last regression, you might see that we were putting in our syntax that we're so familiar with at this point. Here's our syntax. Okay, and when you put the syntax in, there is an option there for you to hit log mode. The purpose of that is right now, by entering that syntax into Desmos, you are getting the top, utmost, best regression that you can get because it's using the most modern technology, the most updated technology that's possible. If you instead choose to use another graphing utility, like for example, a TI-86 or a graphing calculator, otherwise that may be a little bit less than modern for whatever reason, you'll probably get different answers. And if you recall in our last lesson, we got some different answers that were slightly off. And I want to explain to you in this lesson why that happened. The reason why that happened was because in your textbook, they were using a TI-86 graphing calculator to do their regression. We are using Desmos. Desmos does a better job. So instead of the value of 68%, we got 75%, and that was because we have a more accurate view with the technology we have. The point is, if you elect to click log mode when you're doing your regressions, what will happen is Desmos will perform the regression using the older kind of technology, i.e. the same technology the TI-86 is using, i.e. the answers that are in WebAssign and your textbook are associated with that method. So the lesson truly is if you're doing a logarithmic or exponential regression, you should really not click log mode. But if you're going to do practice with our textbook to get your answers, for some of them you should be clicking log mode because those answers were done using an older technology. So here's what I need you to do. When you do WebAssign, play with it. See if the answer is right. If it's not right, try clicking log mode and then use that answer. You have to play around with it to see how you feel about it and also to realize when it's right and when it's wrong to use. I'm going to leave it just like that. Please be advised though, log mode is something that's kind of important. You got to go and click that when it's time to get your answers right and match them up to WebAssign. Okay. All right. So here's a great example of doing a linear regression. I'm sorry, not linear, an exponential regression. Here we have some data on the left. Here we put them in. As you can see, we've entered our syntax and we have a graph. Now, we don't have log mode clicked. Okay, but if you do click log mode, you'll notice the values are slightly different than they were before. Take a look, it's 5337. Here it's 5280. See that they're slightly different, just a tiny bit different, and that's because of that technology giving you a little bit of a better answer. All right. Now, when it comes to doing logarithmic regressions, it's the same idea. So just keep that in mind if you see any extra credit questions anywhere along the line having to do with logarithms, but I don't think that's in your section. Anyway, just remember to try to click log mode when you're playing around with Desmos to use exponential regression. Sometimes it does work and sometimes it doesn't, and you'll learn about that when you're doing your practice in WebAssign, right? So that aside, let's talk now a little bit about exponents and logarithms and how they connect. Starting with the logarithmic form versus the exponential form. Right now, I'm focusing on this particular part of our PowerPoint, where you see cases of logarithmic expressions versus their associated exponential expressions. We've already discussed how they are to be connected, and it's some great examples there. Also, I want to focus with you on some certain special kinds of bases right here. We have common and natural logarithms. A common logarithm is nothing more than a logarithm whose base is 10. And if the base is 10, you'll notice that you don't have to write the 10. You can get rid of that 10, and this is all you have to write is log x. In other words, if you see a log with no base written, you are to assume that it is a common log and its base is 10. Now, when it comes to natural logs, the word natural lends itself to the idea of a base of e, which we discussed in our last lesson. E is an irrational number that was discovered by Euler. It's approximately 2.72. And if you ever feel like you want to write log-based e of x like this, it's not the correct notation. Instead, you should write ln, which stands for log natural. And if you just write ln x, it's assumed that you have a base of e like you see there. So I want you to be familiar with that on a regular basis whenever you see either of these two kinds of writing here, that you know how to interpret them. If it's just a log with no base, you assume it's a common log and that it has a base of 10. If you see the words ln, that means you're doing a logarithm with a base of e, okay? Right now, I'd like to share with you how to do these questions. And we're going to do them on our paper. So again, I'm going to ask you to pay attention to the image, the video. And we'll change over. So first, friends, I'm going to ask you to give me a chance to jot them down. So if you look, you'll see there for A and B, they are asking you to write something that is in one form in the alternative form. Okay. Again, please make sure that your view is toggled to speaker view so that you're getting a good image of this. Right now, you're looking at something here that is in exponential form right here. If it's in exponential form, I can say that this right here is the base. This right here is the exponent. And this right here is the argument. Okay, now the exponent is the log, right? So what we're going to say is the log with a base of 4 with an argument of 64 equals the answer, or the exponent, or the log. This is what you're expected to come up with a solution. Looking at an exponential equation, changing it into a logarithmic equation, it would look like this. It's just a matter of taking the 4 and the 3 and the 64 and moving them to different positions and writing log in the right way. In the same breath, we could do the same thing for this. Here we have a base of 4. Here we have an argument of 1/64th, and we like to call that the argument. And here we have the exponent, or log of 3. So to rewrite this one in exponential form, I'd first write the base, and then write it to the power. That's a negative, by the way. All right. And equals 1/64th is our argument. Okay. So this is great examples of how to move back and forth between exponential and logarithmic format, knowing the connection between them and their relationship. In the next example, they're asking you to find x for a very strange particular equation using a log. 4 equals the log base 2 of x. Okay, so looking at this question, you say, how do I find x? Well, there's a couple of ways you could do it, but the easiest way to do something like this is we're trying to just get your feet wet with logs. So take this equation, which is in logarithmic form, and rewrite it in exponential form and see if you can make sense of it. Here we have a base of 2. We have an argument of x. And here we have an exponent, or log, of 4. So what we could say is the base 2 to the power, or exponent, of 4 equals x. Looking at it now, I think it's clear 16 is the answer here. Does it make sense? Let's see if we write it and it makes sense. The log base 2 of 16 equals 4. Is that true? Is it true that 2 to the what power gives you 16? Yes, 4, right? So that's how we would solve an equation for x that's in logarithmic form. I would encourage you to start by taking the equation, identify the parts of the equation. What is the exponent or log? What is the base? And what is the argument? Then rewrite it in exponential format, because we can understand exponential format a lot better than log. And once it's in exponential format, it becomes very clear. Some students are going to go in an alternative way and say, oh, I can answer this question. 2 to the 4 power is what? Because if I know that it's 4, 2 to the 4 power is what? The answer is 16, you know? So 16 should go here. You can do it that way as well. All right. In the next case, they're asking you to evaluate the log base 2 of 8. It's a very similar approach. For part D, what is the log base 2 of 8? You're asking the question, 2 being raised to the what power gives you 8? The answer is 3. If you weren't sure of that, you could have gone in this direction instead. You could have gone in this direction by saying the log base 2 of 8 equals what? I'm going to call it x because I don't know. And now change that into exponential. Wouldn't that be the base 2 to the power x is going to be the argument, 8. So if I write it this way, maybe now it becomes clear that x must be 3 for that to be true. Okay, so any way you want to look at it, as long as you get 3 as your answer. These are the kinds of things you can't really do with Desmos. And our last case, we have find the log base 5 of 1 over 25. Now, if you're clever about it, you might be able to see that the answer is, after all, -2. But if you could not see that it's -2, put an x in that position and say, okay, our base is 8, our argument is 125, and our actual exponent or log is x. So if that be the case, it would be the idea of 5 to the x equals 1 over 25. And if you have a solid enough grasp on how negative exponents work, you might think in your mind for just a minute, there is a true fact that 5 squared is 25. So doesn't that imply 5 to the minus squared is 125? Any way you look at it, I need you to know that -2 is what belongs there and that your solution for this question is -2. All right? All right. Now, in chapter 5.2, I encourage you to go back and look once more at these cases. These are crucial examples, and they are the foundation of all the stuff you're going to do in WebAssign when you demonstrate your mastery of using logarithms and exponents and stuff like that. This is the elementary piece of it. We should be really comfortable with example 1. All right. Now, for example 2, if we ask you to graph a function, I want to show you how to do that in Desmos. Right now, we're asking you to graph a logarithmic function, log base 2 of x. Now, when it comes to graphing this in Desmos, we're going to run into a little bit of a problem, which is why we need to use what's called the change of base formula, and I'll get to that in a minute. But if you wanted to, you could have done the log base 2 of x cold by using simple number facts. Like, for example, let x be easy numbers like 0, 1, 2, things like that, or 1, 2, 4, and so on, and then also use inverses and things like that to get some values. If you know log base 2 of x is the inverse of 2 to the x, you could have done 2 to the x and just switch the x and y values. But I want to show you also how to use the change of base formula today so that you can get Desmos to graph something like y equals a log base 2 of x. Right. So before we go there, let's do that. Right now, I'm going to show you the change of base formula. Okay, so our goal right now is to graph y equals the log base 2 of x. There is something important that we're going to use here when we're trying to find graphs for logs with odd bases like 2. It's called the change of base formula, and it is going to be in your textbook, and it probably will come up later in this PowerPoint somewhere as well. The change of base formula looks like this. If I'm trying to figure out the log of some funny base with some funny argument, I can choose any new base I like, say, for example, base 10 or base 8. It doesn't matter. Any base. And I'll call that capital B. And I find 2 logs with a base of B. On the top, it's the log of n. On the bottom, it's the log of a. What is the point of this? The point of this is if you're trying to graph the log base 2 of x, you could graph that looking like this. It could be the natural log of 2 over the natural log of x over the natural log of 2, or it could be the common log of x over the common log of 2. And the reason why we would use those instead is because calculators don't have a log base 2 button. They just have an ln button and a log button. Same thing is going on with Desmos, when you look at Desmos, you're not able to come up with interesting different logs with odd bases. Instead, you have to apply this thing called the change of base formula. So instead of trying to type in log base 2 of x into Desmos, I'm going to type in a natural log of x over a natural log of 2, or a log of x over a log of 2 to be able to see those values. Okay, so I have y equals, on the top it will be log x. On the bottom, it'll be log 2. And now if I wanted some points here, see it says undefined for those. And I would expect for it to be undefined because there's nothing to the left of 0 here. There's no negative numbers. But if I wanted to, I could find other special values. Like I understand the powers of 2, so what's it like at 0.5? Or what's it like at 0.125? Or at 0.25? These are all other powers of 2 in decimal format. So if you need them, you can go and get them by putting them in that way. All right? So when it comes to graphing a log on Desmos, with an odd base that is not natural log or common log, you can use the change of base formula as you see here to get your logs in there, okay? All right. Now let's do an application. I'll read it out loud. I'll ask you to try to follow along with me. This is doubling time for an investment application preview. If P dollars is invested for T years at an interest rate R, compounded continuously, then the future value of an investment is given by this formula. The doubling time for this investment can be found by solving for T in the formula. So when S equals 2P, that is, right? That is, you got to change the S into 2P and make it into this formula now. 2P equals PE to the RT. If you divide both sides by P, you get 2 equals E to the RT. Okay, so all of this ridiculous algebra, by the way, when you're all said and done, you have a very basic, nice little formula that we're trying to talk about. The formula, my friends, is right here. All right, I meant to kind of highlight that different. Hold on. There we go. All right. Express this equation in logarithmic form and then solve it for T. Okay, that's not hard to do. So if you want to write it in logarithmic form, then what you would do is you would take this expression the way you see it and change it carefully using the rules that we just discussed about going from exponential to logarithmic. 2 equals E to the RT. Okay, have a look at that. See if we could change it to logarithmic form and then see if we can solve it for T. So first and foremost, if we're going to change this to logarithmic form, here's my base. Here's my exponent or log. And here's my argument. Now, I'll write log and base, the base is E, of the argument, which is 2, equals the exponent or log, which is RT. Now, a couple of little things to fix around here. First of all, log base E, we know what this is. Log base E is natural log. And if we're going to ask you to solve it for T, well, T is over here, and the only thing connected to T is R with multiplication. So use the reverse of multiplication and divide both sides by R. And before you know it, you have a solution. T equals natural log of 2 over R. That's what we were looking for right there. Students might get a little bit confused doing that because they won't realize that RT in its entirety is the whole argument. And as a result, later on, you have to divide out that R. But as you see here, they simplified it. And also, they deliberately switched out that log base E thing, like I told you, and changed it into natural log, which is right here. See how that changed from that to that? So that's important that we get that right. Okay, guys? All right. Okay, now we're going to talk about market share. Suppose that after a company introduces a new product, the number of months, M, before its market share, S, percent model, can be modeled by this formula. When will the company's product have a 35% share of the market? So here, it's kind of important that when you look at this, you know which variable is which. It's telling you that M is the number of months. It's telling you that S is the percent. And we're asking you right now, what happens when S is 35? So take a close look at the arithmetic here. I'm just going to talk about it. We don't have to do it all the way, but you understand how to substitute a number in. But here's what you'll do. Like I said before, this is an example of an application. This one is something that's kind of interesting to us though, because we're business people. But again, this is an application. And as you can see, it's set up just right to just plug the number in and do the math. So S equals 35, put 35 in for S, do a little PEMDAS with a calculator, get natural log. If you want, you can put it all in Desmos all at once, and it will give you that figure 41.6. And that's the answer that we're looking for this one. Now, when it comes to graphing the natural log, again, we have Desmos. We shouldn't have issues with graphing it. I will ask you to go and experiment with it, explore it, go into Desmos, type in y equals e to the x, get a table, get some values, try to get an idea of what it looks like, and just look at it and explore it a little bit. I want it to be that you're not unfamiliar with the natural log of x. It should be second nature if you're in quantitative analysis. And we talk a lot about it in quantitative analysis too. All right. Now, I know that was a lot of fun. I know that you wish we could do even more math today, but that's all I have for you, my friends, for today. So let's take a little bit of a break from our PowerPoint here. I'm going to stop our share. And now I'm going to change my view over to gallery view so that we're all looking together. I'm going to stop our recording, and then we'll open up for any questions or any concerns that you might have. Again, thank you so much for your close attention to my lesson. And I do genuinely appreciate all the work that you guys are putting forward.